Alright guys, good evening. Looks like we don't have audience today also. That is fine. So if you have any questions, you can post in the discussion forum. I will be happy to answer it. And today we are going to see three more problems which is related to ideal gas and real gas using different equation of state to solve a problem. Okay. Yeah. So let's get started. Let's try to solve these three problems today. So the first problem says we have a 2 kg mass of air initially occupying a volume of 0.02 meter cube at a pressure of 8 megapascal, and this expands isothermally and without irreversibility until the volume is 0.08 meter cube. Using the van der Waals equation of state, determine the temperature, pressure and work done during the process. So basically we are not assuming ideal gas here, we are assuming it's actually uh, behaving as a van der Waals, behaving based on van der Waals equation of state. Having said that, let's try to write the given so that we will be able to solve the question. So what was given is, so given we have mass of 2 kg of air, right? Yeah, it looks like we will draw a piston cylinder arrangement. Okay, let me draw that. This is our piston. So initially, this is, let's say, state 1. Let me draw it separately for state 1 and 2. This is state 1. It is expanding, right? This is state 2. During this expansion process, volume increases. So let me draw that. In this case, pressure is also rising. Then maybe, yeah, it's fine. So usually we draw this free piston cylinder arrangement when we go through a piston pressure process. But for now, let's assume uh, this is from state 1 to state 2. Okay, state 1 to state 2 it goes. Let me write for state 1 what are all the things given. So initially it occupies a volume, so let's write volume V1 to be 0.02 meter cube, and the pressure inside is going to be 8 megapascals. Then this expands to a volume of 0.08 meter cube. What has been said is it's an isothermal process, right? So it's an isothermal process without any reversibility. So which means reversible also. Reversible isothermal process. Okay. So since it's an isothermal process, we know there is some T1 and there is some T2, where T2 is nothing but T1 because it's an isothermal process. Right. And then what else? Yeah, so it's going to follow van der Waals equation of state. So let me write down the van der Waals equation of state. I think it should be double A. Van der Waals equation of state is nothing but pressure is equal to RT by V minus V, right? A by V square. Okay. This is the van der Waals equation of state, where V is a specific volume. This is not absolute volume. Please note that. A and B's. What are A and B's? A is nothing but 27 R square TC square divided by 64 PC, and B is RTC by 8 PC. Okay, where PC and TC are critical temperature and pressure for a given gas. In our case, the gas is air. Okay, so gas is air. So we already know critical temperature and pressure for air, or you can refer to tables. It is going to be, temperature is going to be 133 Kelvin and pressure is 37.7 bar. Okay. Now I think everything is defined. A and B is defined. What you need to do is you just need to substitute A and B inside this equation of state, and then try to find all the questions. Yeah. Alright, so let's first find the temperature. So we are asked to find temperature. Okay. Let's do, so now let's find A and B also before finding temperature, so that it simplifies our calculation. A is going to be 27 into, what is R? R is a universal gas constant, which is 8.314 joules per mole Kelvin. Okay, and substitute it here, times 3 square divided by 64 into 37.7 into 10 power 5 bar. So since it's a bar, you just need to multiply by 10 power 5. How much is it coming out to be? 27 into 8.314 square, 4 divided by 37.7. A turns out to be 0.1368. Okay. Similarly, let's find B. B is nothing but RTC by 8 PC, which is 8.314 into TC 133 7.7. Just for the sake of completeness, let me write it down separately. Divided by 8 into 37.7 into 10 power 5 divided by 10 power 5. E turns out to be 3.666 into 10 power minus 5. And now we can rearrange this van der Waals equation of state to find temperature. So that is going to be RT by V minus V is equal to P plus A by V square, which T is nothing but V minus B by R into P plus A by V square, which is equal to, now we need to find, let's say at state 1. Okay, so state 1 temperature T1 is going to be V1 minus B by R times P1 plus A by V1 square. Okay, so what is V1? V1 is nothing but, we had a volume 0.02 meter cube. Since this is a specific volume, it's nothing but volume divided by mass, right? So 0.02 divided by mass is 2 kgs is equal to 0.01 meter cube per kg. Okay, now P1 is already known, which is 8 megapascal. Now let's substitute these relations inside. It's going to be 3.666 into 10 power minus 5, 8.314. P, which is 8 megapascal, 8 into 10 power 6 plus A, which is 0.1368, 0.01 whole square. Let's find out what is temperature. 3168 divided by 0.01 square into 10 power 6 to 0.01 minus 3.66 into 10 power minus 5 divided by 8.314. I am getting around 958 Kelvin. Let me check the calculations again. Let's check the calculations of A and B. Did we miss something here? Is 27 by 64. Taking May. Let me correct it. E. This in terms of kilojoules per kilomole Kelvin, right? So we to multiply by 10 power 3 whole square is going to be 10 power 6. 10 power 3. Try it again. 27 into 314 square power 6 divided by 6 divided by 31.5 power 5. So yeah, there's going to be into 10 power 6 factor here too. 1.36 825. It's a very big number, and here also it's going to be just if you 3 here, it's going to be 10 power minus 2. Now let's substitute it properly over here. It's going to be 10 power minus 6 136,825. Think we will get correct answer. 5 divided by 0.01 square plus 18 to 10 power 6 divided by 8314 101 minus 3.66 into 10 power 0.01 meter cube per kg, right? So it is 0.02 divided by 0.01 meter cube per kg. Check the constants again. So let me write down the units too. So let's see, 314 is joules per kilomole Kelvin. So square, right? Joules square kilomole Kelvin is Newton. So cancel these two. So joule is Newton meter. So Newton meter, meter square, right? Meter power 4. Right. Yeah, Newton meter power 4 divided by kilomole. So power 4 divided by kilomole. And similarly here, it's going to be joules per kilomole Kelvin times K divided by Newton per meter square. Okay. Joule is nothing but Newton meter. Then Newton gets cancelled, so it's going to be meter cube per kilomole. Okay, like that. Here also, this is going to be meter cube per kilomole. These two are right. Now, if you substitute it here, you will get kg per kilomole. So P and A by V square should have same, units. So what is here? Newton meter power 4 divided by kilomole. So let's say Newton meter power 4 by kilomole square per cube per kg meter power 6 kg per meter cube per kg square, and this you can replace with 2 meter square. Newton per meter square is pascals, right? Kg square by kilomole. Additionally, why there is 7? Okay. So if this is for A, right? Let me check. Right only. Mm, V is going to be meter cube. Oh, it's since you are writing in terms of moles, it should be in terms of moles. If you are writing in terms of kg, you need to change the units, right? So okay. So this part, that is why the problem is. Okay. So since you wrote everything in mole, you should write V also in terms of mole. This V1 is in terms of okay, let's just write it. Since it's in the molar basis, let's put a bar over here so that we will understand it's a molar basis. And so this V is not just 0.01, it's something else. So temperature is also wrong. So let me find V for a mole. Okay. So what we know about the molecular weight of air we know, which is 28.9, right? 20. What is molecular weight of air? Sorry, I forgot. Okay, 28.9, right? 28.97 kg per kilomole. Now V bar is nothing but we need to write V also in terms of kilomole, right? So we have to multiply by regular weight so that we get meter cube per kilomole. Now let's say you do that 0.088.97, which is equal to 0.01 into 28.97, which is 0.2897. Oh, okay, 2897 meter cube per kilomole. So that's why units are important. Whether it's a molar basis or mass basis, you should be very careful. Anyway, 0.2897 in here also 0.2897. Everything is in terms of kilomole basis. So now it shouldn't create a problem. Let me see. 0.2897 minus 3.66 into 10 power minus 2 divided by 8.31. Okay. This part is 0 into 136825 divided by 0.289 into 10 power 6. This is around multiplied by 0.0304. So to be temperature is 292.76 Kelvin. So this is T1. Okay. So T1 is this. Gives me reasonable value. Please check whether it is a right value or not. Anyway, this is the T1, and since it's going to be an isothermal process, T2 is going to be same as T1 isothermal process. T2 is going to be 292.76 Kelvin. So basically what is our next? So temperature we found, which is 292 Kelvin. We should also find final pressure. So basically since it's an expansion process, pressure we should expect to be lesser, right? Let's try. Again, P is equal to RT by V minus P. T by V minus A by V square. I hope. Yeah. So now we need to know the final pressure. So it's a state 2. So for state 2, P2 is going to be RP2 divided by minus B minus A by V2 square. Let's find V2. V2 is nothing but 0. Which is nothing but final volume by mass, which is going to be 0.08 by 2. I think it's 0.08. Yeah, 0.08 by 2, which is 0.04 meter cube per kg. Okay, and similarly V2 bar, which is nothing but V2 into the rate is 28. Let's multiply 0.04 into 28.97. So kg per kilomole. So when you multiply it, you will get 1.1568. So usually some people also write instead of meter cube per kilomole, they try to use meter cube per mole. You could try that also. This is going to be 8.314 in 10 power 3 into T2, which we just found 292.76 divided by 1.1568 minus 3.66 into 10 power minus 2 minus A is going to be 136, a very big number, 825, divided by 1.1568 square. The moment of truth. Let's see, 8314 into 292.76 divided by 1.1568. 8 minus 3.22 into 10 36825 divided by, so it is coming out to be 2.06. It is coming out to be, let me write that down, 2.0608 around into 10 power 6 pascals. So which is around 2.06 megapascals. So my initial pressure was 8 megapascal. Pressure reduced to 2.06 megapascal. Now it looks like the calculations are right. Okay. Now let's try to answer the final question, which is what developed in the process in kilojoules. Okay. What is the work developed? See, work, it is nothing but integral of PdV, right? From 1 to 2. And let's substitute this P for P. It is nothing but RT by V minus B minus 2. Just rearrange. It's going to be integral 1 to 2 dV minus integral of 1 to 2 square dV. It's just simple integration. Since T remains constant, R is universal gas constant. These two can go out. Again, B is also a constant. So you can write this as ln of V minus B 2 minus this is going to be 1 by V square is A times 1 by V 2 plus 1 divided by minus 1. V2 minus P minus P minus 1 divided by V2 minus 1 divided. This can also be written as V2 minus P by V1 minus B. A times 1 divided by V2 minus 1 divided by V1. This is the total work done. Okay, let's just quickly substitute all the. And one more thing. Yeah, what is this work done? What is the unit of this work done? We need to evaluate. Let's see. So 8.314 into 10 power 3. Temperature we kept constant, right? What is the temperature? 297 or something, 76. We can just simply write 293 also, no problem. V2. Uh, again, this is going to be in molar basis, so all these are in molars. Then work done also will be in kilojoules per mole, right? And then you need to take into account of the mass, how much amount of mole, how many moles are contained in that 2 kg mass. And once you multiply that, then you will be able to get the total work done. We will come to this V2 we just found 1.1568. 1.158 minus B 3.66 into 10 power minus 2 divided by V1, which is 0.2897 into 10 power minus 2. Alright, A, which is going to be the big number, it's 136 825 into 1 divided by V2. V2 is nothing but 1.158 minus 1 divided by V1, 0.2897. Okay, let's see what this gives us. So first term is going to give me 1.156 into 10 power minus 2, 0.2897 minus 3.6 into 10 power minus 2. Alright, and law of answer times 292. 314 into 323, sorry, 3620.53 into 10 plus 36 825 divided by 1.1568 67, sorry, 2897. 354.023. So total 3266.5 into 10 power 3. Now what is the unit? Unit is going to be work out. So both of these units is going to remain same, right? Yes, it's power 4 by kilomole 1 divided by V, which is going to be meter cube per kilomole. So kilomole. This in kilojoules. A, what is the unit of A? Where did I write A? Here. This in, right. So A by V square. So this should be kilomole square, no? Just it here. Then only you will get. Okay. Now since it is kilomole square, you just will be kilomole square. So this will be going. So it will be meter per kilomole, which is joules per kilomole. This is joules per kilomole. So this is the work done. So since it's in molar, we'll just put a bar over here. Now the total work done is going to be number of moles, which should be in kilomole, times the this thing. So how do you find number of moles? Number of moles can be found is divided by molecular weight is 28 kg per kilomole into 3266.5 kilojoules per kilomole. So the total will be just become kilojoules. Let me just multiply this divided by 28.9. So yeah, 225 point. So the total work done turns out to be 225 point kilojoules. Okay. So this is a problem with real gas. It requires lot of calculations. It's better to write a program once and then use that program again and again. Anyway, this is just for a practice for you to show how you can calculate, let's say, work done for a real gas. So what if I use ideal gas? Then my pressure and temperature would be different. So work done also would be different. Okay, well, you can try it. You can try and let me know. Ideal gas. So probably my guess is the work done would be lesser for an ideal gas. Ideal gas. Or the work output in this case. Yeah. Let's see. Yeah, you can give it a try and let me know. And since this is an expansion process, you are taking work out of it. So work coming out to be will be more actually. Yeah, since you consider it as an ideal gas. In a real gas, you may not end up getting that much work. All right, you can check that. Now the second question is derive the expression. So I am using Van der Waals equation of state in this session. There is also Reddy's equation of state. You can also try that. But as I said, the complications will be even more if you use that equation of state. It is actually even a non-linear equation of state. Non-linear in terms of all the equation of states are non-linear, but It has, let's say, if you want to find temperature from pressure and volume, you will be having two terms containing temperature. So you need to come up with a numerical method to solve it. So it will be a little complicated. That's why I didn't take that equation of state. Anyway, um, let's solve the second problem. Derive expression for delta U, delta H, delta S for a gas that obeys Van der Waals equation of state for an isothermal process. Again, the process is isothermal, which is important. So temperature is constant during that process. So you are asked to find what is the change in energy, internal energy, enthalpy, and entropy if it's an isothermal process. So let's just find the change in internal energy first. So we already know the internal energy equation, right? So du is nothing but cv dt plus T times dou P by dou T at constant V minus P times dV, right? And this is, since it's an isothermal process, this will go away, right? Isothermal. We are trying to do is we are simply integrating. So delta U is nothing but U2 minus U1, which is nothing but integral of du from 1 to 2. This also can be written as integral from 1 to 2 t dou p by dou t at constant v minus p times dv. So now we know the equation of state, which is nothing but r by t v minus p minus a by v square. So let's try to find out those derivatives. Dou p by dou t at constant v is going to be so we are differentiating in terms of temperature, so there is only one term, keeping v as a constant. Now let's multiply this. T dou p by p is going to be rt by v minus p minus p. You can substitute to the from the equation of state, rt by v minus into minus plus a by v square. So this and this gets cancelled, so only a by v square remains. Substitute that in del u. So del u is nothing but integral of 1 to 2 a by v square dv. This turns out to be simpler, which is going to be so it's going to be simply a into 1 by v1. This is the change in internal energy you will get when you have an isothermal process for a gas which obeys Van der Waals equation of state. Let me just box it out. U is going to be times 1 divided by v1. Yeah, the next one is delta H. H. Again the same thing, we have enthalpy equation which we already know. R, yeah, again H is nothing but U plus PV, right? So dH you can write like du plus d times, to find delta H, which is H2 minus H1, which is equal to integral of dH from 1 to 2 plus integral of 1 to 2 times PV, which is nothing but delta U plus integral of 1 to 2 d. I'm just using a shortcut to do it. You can even write a dH equal to Cp dt, that full equation, and you can is going to be delta U, we already know, which is nothing but 1 divided by plus dPV, right? So PV, change in PV, that's it. So P and V is going to change, so it's going to be nothing but P2 V2. So this you can simply write PV. This you can rewrite this as delta H is going to be A times 1 divided by V1 minus 1 divided by plus P2 V2 minus P1 V1. Yeah, delta H was simple. The next one is delta S. Delta S. How do we find the entropy change? So similarly, we use the same. When we use the equation entropy change in entropy, which we already know. It's CV by T dt plus dou P by dou T at constant P dV. So if you remember it, you just uh, take the total derivative of this into total change in entropy as a function of function of V and T, right? T and V, and just expand it, apply the solve relations, and you will end up getting this equation. And this equation we already discussed, right? So yeah, now we need to substitute this here. Again, since it's an isothermal process, we can neglect this. Isothermal, there is no CPCVs here, and dP by, so only this term will be left. What we need is delta S, which is again S2 minus S1. This is integral of ds from 1 to 2, which is equal to integral of 1 to 2 dou P by dou T at constant V dV. And I think we already found dou P by dou T at constant V. Yeah, here it is. So we just use this R by V minus V, right? Is equal to integral of 1 to 2 R V minus B dV. We could have actually we could have used the TDS relation also to find this. It's fine. It's going to be R of ln V minus P is equal to R times ln V2 minus B minus is going to be R V2 minus B by V1 minus B. Alright, so this is our change in entropy. So this looks like the ideal gas equation's entropy, only that this B's are coming here. Similarly, since it's an isothermal process, this part you may not end up getting. So for an isothermal process, and delta H, again this part will remain. Okay. So yeah, that's it, right? So we found delta U, delta H, and delta S for the gas. Go to the third question. This is an interesting question. Show that the enthalpy of ideal gas is a function of temperature only, and that of an incompressible substance it also depends on pressure. So there is The ideal gas is ideal. The enthalpy of ideal gas is only the function of temperature. It doesn't depend on pressure or other independent variable. It is just a function of temperature. And for an incompressible substance, in addition to the dependence on temperature, it also depends on pressure. Right? We need to show that. So for that, we can use the uh, equation for enthalpy, which we already derived. Let's start with that. So it's going to be dH is equal to Cp dt, if I remember correctly, and there will be additional uh, term for dP, right? So that is nothing but V minus T into dou V by T at constant P dP. Okay, so this is the change in enthalpy for any gas. Since we are dealing with ideal gas now, we need to show that enthalpy is a function of temperature only. So ideal gas, we know it's going to be PV is equal to RT, right? So let's say if I rearrange this, V is equal to RT by P. So let's try to find out this term dou V by dou T at constant P. So which is nothing but by P, right? So this whole term V times T dou V by dou T by a constant P is going to be P is nothing but RT by P minus R. Whole thing becomes 0, right? Okay, so I think it should be right. So this whole thing becomes 0, this whole thing. Then the enthalpy left with is nothing but Cp times dt. But so dH is Cp dt, that is what is given. But it doesn't prove that enthalpy is a function of temperature only. So this Cp could be a function of temperature, right? Cp could be a function of temperature. Now we need to establish that Cp is also not a function of temperature. Sorry, Cp could be a function of pressure. Pressure and temperature. Now we need to prove that Cp is not a function of pressure, it is just a function of temperature. Let's see. To prove Cp is function of temperature only. So how do we do that? So you can go back and recall this relation where we wrote by dou P constant temperature is nothing but minus T times square by dou T square. If you want, I can go back and check my notes from where this relation came. Just about Cp over here somewhere. So Cp by dou T is about Mayer relation. You would continue from there. Yeah, I think I didn't write this. So separately about Cp, we would have wrote something. Back and check your notes. This relation. So if we prove that dou Cp by dou P is equal to 0, then Cp is not a function of pressure. Right. So for that we need to know dou V by dou T at constant P, that we just found out, right? Dou V by dou T at constant P is nothing but R by P. r by p. Now this is a constant. Now this is a second derivative, right? So dou square v, here it should be dou square v by dou t square. It's going to be, since it's not a function of let me see, times r by p, right? Since r by p is not a function of temperature, so this part is going to be 0. And since if you substitute here, dou Cp by dou constant temperature is going to be simply 0, which means Cp is not a function of pressure. So then Cp could be function of only temperature. So then if that is the case, is equal to Cp, which is a function of temperature, and dt, right? So this proves that h is a function of t only. Since Cp is also a function of temperature and there is a derivative of temperature, so h could only be a function of temperature. So that is proven. And for an incompressible substance, it also depends on pressure. Okay, so what is an incompressible substance? So how about substance? Incompressible substance, we know one thing about incompressible substance, which is the volume constant. This is like an equation of state for an incompressible substance. So if V is constant, then what happens? Let's go back and look at our equation. dH equal to Cp dt Cp dt plus E minus T of dou V at constant P dP, right? Since V is a constant, dou V by dou T at constant P is going to be simply 0 because V is constant. And since that is 0, so dH is going to be Cp dt plus dP. So you cannot simplify it even further, right? Since you have a dependence on pressure, here you no need to check whether Cp is a function of temperature or pressure. So we just need to prove that H is a function of both T and P, right? Since you already have VdP term, so it is going to be a function of pressure. Now you no need to worry whether Cp is a function of temperature or pressure. So let's say if you want to know, you can use the same thing. And you would see that dou V by dou T, right? Since V is a constant, this part again goes to 0. So finally you will end up having Cv as a function of only temperature. And even though if you substitute it as Cv is a function of temperature, you have additional term which is from where pressure dependent comes. This proves that H is a function of both temperature and pressure. H is a function of both temperature and pressure. Right? So in this way you can prove that incompressible function, the enthalpy is a function of both temperature and pressure. But for an ideal gas, it is going to be a function of only temperature. All right. I think that's it for today. I think we took quite a lot of time. I mean, I took a quite time in solving the first problem because of the unit mismatch. So please don't do that mistake again. Right? So you also please don't do such mistakes. Uh, Follow units properly so that you will end up getting proper results quickly as possible. Yeah. So if I want to quickly recap what we did, we solved three problems. In which, two of the problem deals with equational state, and let's say if you want to find what is the work developed during expansion of a substance, you given that substance is going to behave based on Van der Waals equational state, then how do we find it? So it's just merely applying equational state to find pressure, temperature, and using it to find the work developed. Right. So this is quite easy. And the second question we dealt is we for an ideal gas equational state we know change in internal energy, enthalpy, and entropy relations. But if it's a different equational state, let's say Van der Waals equational state, how do we find it? So similarly, it can be applied for any equational state. For example, if you just need to use this equation, you substitute your relation, and you end up getting the change in internal energy, enthalpy, and entropy. uh, but remember, it's for an isothermal process, so we neglected this cv dt, so any dt term we neglect. So based on that you can find all the parameters. The third one, we established that enthalpy for an ideal gas is a function of only temperature. So this will be useful um, in subsequent topics when we discuss. And also for an incompressible substance, we know that V is constant. So at that time, enthalpy depends on both temperature and pressure. We proved it. All right. By this, I will conclude this session. If you have any sessions or if you want to share any comments about this questions, if you have any doubts, you can contact me through the discussion forum, and please post your questions there. I will be able to answer, or you can come back or next week and discuss those questions. All right. See you next week. Bye.